Microchips have become one of the most significant inventions of modern times. Without them, smartphones, computers, and most modern medical devices wouldn't work. They are so small that we usually don't even notice them, yet they play a key role in our everyday lives. How is this miniature technology made? And what will change when the new generation of chips arrives? In this episode, we'll go behind the scenes of their production and reveal why there can be no future for artificial intelligence or quantum computers without them. A microchip is a small integrated circuit that contains millions to billions of transistors. To understand its complexity, let's imagine it magnified 500 times. Individual areas with specific functions are connected by ultra-thin copper conductors, whose total length can reach up to hundreds of kilometers. At the bottom of the chip, there are billions of electronic components that create digital signals flowing across the entire structure. The most common component on the chip is the transistor, a semiconductor switch that allows the flow of electric current depending on the applied voltage. The size of transistors can be as small as 20 nanometers, and a single chip can integrate more than 50 billion of them. Globally, we produce more than 1 trillion computer chips each year, which means approximately 20 trillion transistors every second. And all of this is managed by less than 500 factories worldwide. How can we make so many small and intricately connected devices so incredibly fast? The answer is a technology called lithography, which allows all the microscopic circuits to be produced at once. The main material from which chips are made is silicon, which is obtained from ordinary sand. Silicon must first be purified and melted into a monocrystalline form from which thin wafers are cut. These form the basis of every microchip. Photolithography is a process in which a special photosensitive layer called photoresist is applied to the surface of a silicon wafer. Ultraviolet light is used to project a pattern onto the circuit through a mask, similar to projecting a slide. The illuminated parts are then chemically removed, and reactive gases etch the exposed areas, transferring the pattern onto the actual wafer. Into these prepared areas, ions of boron or phosphorus are introduced, tiny particles that change the conductivity of silicon. Thanks to this, transistors are created, the basic building blocks of computer chips. Because each additional layer leaves slight unevenness, the surface must be perfectly smoothed after each step using fine chemical mechanical polishing. This complex process must be repeated more than 100 times to create a complex network of circuits connecting memory, computational cores, and other parts of the chip. The production of a single chip takes approximately 3 months and occurs in an extremely clean environment where the air is constantly filtered and a vacuum similar to that in space is maintained. The entire process consumes a large amount of electricity, water, chemicals, and rare gases. Up to 20 liters of waste is generated per single wafer, which must be thoroughly cleaned. And because photoresists contain so-called forever chemicals, which decompose poorly, new ecological challenges arise. The production of microchips is strategically important for geopolitics. World production is concentrated among a few giants, dominated by the Taiwanese company TSMC, South Korean Samsung, and American Intel. The European company ASML is a key supplier of the most advanced machines for technology that uses extremely short wavelengths of light to produce the smallest and most powerful chips today. The sponsor of this channel is Buddy, your mentor and AI friend. Just enter Buddy FM and you can try it for free. With the growing demand for more powerful chips, we are hitting not only the limits of sustainability, but also the possibilities of further performance increases. The current generation of microchips is also reaching its physical and technological limits. As transistors shrink below the threshold of a few nanometers, the risk of power leakage, overheating, and manufacturing errors. The production of such advanced chips is not only extremely expensive, but also technologically demanding. At the same time, there is a slowdown in the so-called Moore's law, according to which the number of transistors on a chip doubles every 2 years. Today we are approaching physical limits where further miniaturization starts to collide with the laws of quantum mechanics. That is why alternatives are beginning to emerge. One of the most promising is photonic chips, which use light instead of electrons to process information. Photonic circuits can be significantly faster and more energy efficient, especially for data transmission over short distances, such as between processors and memory. Additionally, they generate almost no heat, consume less energy, require less cooling, and have a longer lifespan. Another advantage is the ability to transmit multiple signals simultaneously using different wavelengths of light, which allows for efficient parallel computations. Startups like Lightmatter are developing them for accelerating artificial intelligence, and they are also used in research projects by Google, Intel, or MIT. Additionally, the company Lightmatter recently introduced the breakthrough system Passage, which transfers data using light directly under processors. Electrical signals are converted into laser beams that propagate through optical fibers at the speed of light without resistance and losses. The result is up to 20 times lower energy consumption compared to copper conductors. This technology could fundamentally change the performance of future data centers, which will need thousands of chips collaborating on complex computations. The company has already secured investments over $800 million and plans the first deployment by the end of the year 2025. Electronic chips are still cheaper and sufficiently powerful for common devices. However, in areas such as machine learning, quantum simulation, or working with large volumes of data, photonic chips have enormous potential, not only due to performance, but also thanks to significant energy savings. Another direction of development is represented by chips based on new materials, such as graphene or so-called two-dimensional semiconductors. The development of specialized architectures designed specifically for artificial intelligence or quantum computing also plays a significant role. These technologies are not yet ready for mass production, but show the path development may take in the coming years. Microchips will continue to be one of the main pillars of technological advancement. As system complexity increases, and with the development of artificial intelligence and autonomous technologies, the demand for their performance will also grow. The future thus belongs not only to smaller and more powerful chips, but also to smarter designs that utilize new principles of operation. For more content about future technologies, click like and subscribe. And don't forget to tell us your opinion on the future of microchip manufacturing.